This is submodule 2 of 3 on formation evaluation, MWD, LWD, and mud logging. In the first submodule, our focus was on MWD technologies. In the second submodule, our focus will switch to LWD technologies. So let's begin. Let's introduce what LWD is. The key point to remember is that LWD provides formation evaluation data while the well is being drilled, eliminating the delays of traditional wireline logging. The tools themselves are equipped with onboard memory, which stores all the high-resolution data collected downhole. A portion of that data is transmitted in real time through the MWD telemetry system, allowing the drilling team to monitor formation changes instantly. This real-time stream is sufficient for directional drilling, well placement, and initial formation evaluation. Once the tools are back at surface, the remaining detailed data is downloaded, giving a full picture of the wellbore environment. Power for these tools usually comes from the MWD system, although many have backup batteries to ensure reliability. Importantly, the memory is non-volatile, meaning data is preserved even if circulation stops or power is interrupted. A wide range of LWD services are available. The most common is resistivity, but others include porosity, sonic, and caliper measurements. Together, these services help determine lithology, compaction, fluid content, and reservoir quality, ultimately supporting safer drilling and better production outcomes. This slide gives an overview of the different measurements that can be acquired using logging while drilling tools and how they contribute to formation evaluation and identification. Each measurement adds a piece to the subsurface puzzle, allowing us to make informed decisions while the well is being drilled. First, resistivity is one of the most fundamental logs. It measures how strongly the formation resists electrical current. Hydrocarbons are poor conductors, so zones with high resistivity are often associated with oil or gas. By contrast, water-bearing formations with saline fluids show low resistivity. Gamma ray is used to distinguish between shales, which are radioactive, and cleaner formations such as sandstones or limestones. Low gamma readings indicate reservoir potential, while high values highlight shales or non-reservoir intervals. Neutron density, often paired with density logs, is used to determine porosity. Neutron logs respond to hydrogen content, while density logs measure electron density. Together, they help us quantify pore space and identify gas through the characteristic neutron density crossover. Sonic measurements provide acoustic velocities, which can be used to predict pore pressure and mechanical properties of the formation. This is essential for wellbore stability and safe drilling. Caliper logs track borehole size and shape, identifying washouts, breakouts, and rugosity. This information is used to calibrate the density and porosity measurements, which only measure a short distance into the formation and can be heavily affected by washouts and borehole rugosity. Formation pressure while drilling measures the fluid pressure directly in the formation. This is a key input for petrophysicists. APWD, or annular pressure. While drilling monitors pressure in the annulus and can be used to monitor hole cleaning efficiency and potentially give an early kick warning sign. Finally, seismic while drilling integrates LWD data with surface seismic, enabling formation mapping ahead of the bit while drilling exploration wells. This is often a tool used in deep water exploration wells. This illustration shows a typical Baker Hughes logging while drilling bottom hole assembly, with the tool modules arranged sequentially along the drill collar. Let's walk through the measurement suite from the bottom upwards, because the order of these sensors is intentional and directly tied to data quality and operational performance. Starting at the bottom, just above the bit, we see the gamma ray detector. Gamma ray must be as close to the bit as possible because it provides the first indicator of lithology, allowing geologists and directional drillers to identify shale and sand or carbonate changes quickly. Having this measurement near bit supports real-time geosteering decisions. Moving slightly higher is the inclination package. This contains accelerometers, enabling improved steering accuracy, especially when geosteering. Next, we encounter the resistivity module. Resistivity provides formation evaluation by differentiating between hydrocarbon-bearing and water-bearing zones. Above resistivity is the density tool. This uses a pad or standoff sensor pressed against the borehole wall to measure electron density, which is converted into formation bulk density. Density is essential for porosity determination and lithology discrimination. Midway up the string, we see the acoustic standoff sensor. Its role is to monitor how well the density pad maintains contact with the borehole wall, ensuring accurate calibration and reducing the effects of borehole rugosity. Near the top of the measurement section sits the neutron porosity tool. It emits high-energy neutrons and records the hydrogen index of the formation directly linked to porosity. Placing it above density reduces interference between the two measurements. Altogether, this BHA integrates directional, lithological, and petrophysical measurements, delivering a comprehensive formation evaluation picture while drilling, enabling the operator to make faster, better informed decisions in real time. On this slide, we're looking at the main types of resistivity tools used in logging while drilling, or LWD. These tools measure the electrical resistivity of formations, which is one of the most important measurements for identifying hydrocarbons. The first type shown is the short normal resistivity tool. This gives us qualitative indications of hydrocarbon zones. It's often used for selecting coring points, particularly with sidewall coring. It also helps predict pore pressure in undercompacted shales, which is critical for safe drilling operations. In addition, it assists with casing point selection and qualitative hydrocarbon detection. Next, we have the 2 MHz resistivity tool. This provides the same features as normal resistivity tools, but goes further by delivering quantitative petrophysical measurements, whether we are in water-based mud, WBM, or oil-based mud, OBM. It is particularly useful for identifying zones of high and low permeability, giving us greater insight into reservoir quality. Finally, the focused resistivity tool. This works in a similar way to the 16-inch normal resistivity measurement, but is designed to work effectively in conductive drilling fluids, such as salt-based muds. This slide illustrates 2 critical applications of logging while drilling measurements, assessing borehole geometry and determining casing points. On the left, the circular plot shows borehole shape measured by LWD calipers or imaging tools. Ideally, the borehole should remain close to its nominal gauge, producing a near-perfect circle. In reality, stresses in the formation often cause breakouts, enlargements, or ovalization. The irregular shape seen here, with elongation along certain azimuths, indicates stress-related breakout. This information is invaluable because it reveals the orientation of the in-situ stress field and highlights potential instability zones. By monitoring borehole geometry in real time, drilling engineers can adjust mud weight, bit selection, or trajectory to reduce instability risks. On the right, we see a log comparison between the current well and an offset well. The tracks display key properties such as resistivity and gamma ray, which are used to identify lithological boundaries and fluid contacts. By correlating these log responses, geoscientists determine the most appropriate casing depth. Notice how specific features, sharp resistivity changes or gamma ray shifts, are aligned between the 2 wells. These correlations ensure that casing is set above problematic formations such as weak shales or high-pressure zones, while still maintaining access to target reservoirs. This slide shows a logging while drilling suite, which is one of the most powerful tools we have for formation evaluation while the well is being drilled. The data you see here is acquired in real time and transmitted to surface, allowing the drilling and geology teams to make decisions quickly and confidently. The 4 main curves presented are gamma ray, resistivity, neutron porosity, and density. When we read them together, they provide a multi-dimensional view of the reservoir. Let's start with the gamma ray. A gamma ray measures natural radioactivity, which is mainly associated with shales. In this log, the gamma ray baseline is relatively low, which suggests we are drilling through clean carbonate intervals. This is consistent with the note on the slide that the reservoirs are limestone deposited in a marine environment. Next, look at the resistivity tracks. Where resistivity is high, the formation resists the flow of electrical current. This is a strong indicator of hydrocarbons because oil and gas are non-conductive, whereas saline formation water is highly conductive. Several resistivity curves are shown, each with a different depth of investigation. This enables petrophysicists to calculate the true resistivity of the formation. The upper track, which displays density and porosity, has its scales set up so that the curves align with each other when in limestone. Notice how the highlighted yellow zones align with the high resistivity readings. Neutron porosity responds to hydrogen content, while density porosity measures bulk electron density. Where these two curves overlay closely, the porosity measurement is reliable and fluid-filled. However, where we see a crossover, with the neutron curve reading higher porosity than density, this can suggest the presence of gas. The log shows several such intervals, reinforcing the interpretation that we may be looking at gas-bearing limestone. This slide demonstrates how logging while drilling data can be used in combination with measurement while drilling measurements to detect water influx in the wellbore. What you see on the log are multiple tracks that record different properties of the formation in real time as drilling progresses. The focus here is on resistivity, which is one of the most reliable indicators of fluid type in the pore space. Resistivity measures how strongly the formation resists the flow of electrical current. Hydrocarbon-bearing zones typically show high resistivity values because oil and gas are poor conductors of electricity. By contrast, water-bearing zones, especially if the water is saline, show much lower resistivity because brine is highly conductive. On this log, you can clearly see intervals where resistivity drops sharply, highlighted by the blue-filled sections. These drops signal water-bearing formations or water influx zones. Gamma-ray tools measure naturally occurring radioactivity in the formation. Most gamma radiation comes from potassium, which is abundant in clay minerals. This makes the gamma-ray log particularly effective for distinguishing between shales, which are radioactive, and non-shale reservoirs such as sandstones and limestones, which are typically cleaner. Additional contributions to gamma-ray readings may come from uranium, often deposited in water-bearing formations, or thorium, which is also found in clays. Modern spectral gamma-ray tools can differentiate between potassium, uranium, and thorium based on energy distribution. This adds detail beyond a conventional gamma-ray tool, allowing for improved geological interpretation and correlation. The primary uses of gamma-ray logging while drilling include shale identification, estimation of clay content in sands and carbonates, and correlation of real-time data with offset logs to determine the geologic location of the well. Gamma-ray is also useful for picking casing depths and coring points, as it clearly identifies changes in lithology. However, gamma-ray tools have limitations. Count rates are time-dependent, which means at high rates of penetration, the data can be truncated or smeared. This requires careful calibration and quality control to ensure reliable interpretation. This slide introduces the neutron porosity tool, one of the most widely used LWD measurements for estimating porosity while drilling. The tool works by emitting high-energy neutrons from a radioactive source into the formation. These neutrons collide with hydrogen nuclei, which are very effective at slowing them down. Once slowed, neutrons are either captured, releasing gamma rays, which are then detected by the tool's receivers. Since hydrogen is primarily present in pore fluids, oil, gas, or water, the count rate at the detectors is directly related to formation porosity. Now let's look at the picture labelled Figure 6. The diagram shows a schematic of the neutron porosity tool layout. At the bottom is the neutron source, which projects neutrons into the surrounding rock. Further up the tool are two detectors, typically referred to as the short-spaced and long-spaced detectors. The short detector is closer to the source, making it more sensitive to borehole and mud effects. The long detector is further away and provides a truer measure of formation response. By combining the two, the tool compensates for borehole irregularities and fluid variations, producing a more accurate porosity estimate. On interpretation, neutron porosity logs are typically read alongside density logs. Where neutron and density overlay, the porosity reading is reliable. However, when the neutron curve reads much higher than density, we often see the crossover effect, which is a strong indicator of gas. In shales, neutron porosity can overestimate porosity because bound water in clays contains hydrogen, which the tool responds to as if it were fluid-filled pore space. The neutron porosity log is most powerful when combined with other measurements. When interpreted alongside density logs, it allows us to calculate porosity more accurately and to distinguish between lithologies using crossplots. For instance, in carbonates, the relationship between neutron and density helps us identify limestone, dolomite, or sandstone. Another critical use is in gas detection. When neutron porosity reads much higher than density, the crossover strongly indicates gas-bearing intervals. The tool can also be used on its own for quick porosity estimation while drilling, especially in cleaner formations. The neutron tool also has limitations. Its shallow depth of investigation makes it sensitive to borehole washouts and mud conditions. Shales can cause overestimation of porosity because bound water in clays contains hydrogen, which the tool interprets as pore fluid. Also, while it is quick to deploy, it cannot reliably distinguish between hydrocarbons and water without support from resistivity or density measurements. This slide focuses on the formation density log, a key component of logging while drilling services. The purpose of this tool is to measure the bulk density of the formation, which we can then use to calculate porosity, identify lithology, and support pore pressure prediction. A radioactive source at the tool emits gamma rays into the surrounding rock. These gamma rays interact with electrons in the formation. As they collide, they lose energy, scatter, and are eventually absorbed. Two detectors, one short-spaced and one long-spaced, are positioned above the source. They record both the number and the energy of the scattered gamma rays. The count rate received at the detectors is directly proportional to the electron density of the formation, which in turn is proportional to the bulk density of the rock. By comparing the two detectors, the tool corrects for borehole effects such as mud cake or small irregularities in borehole smoothness. The uses are very similar to the porosity measurement. Additional density measurements are also used in predicting pore pressure as undercompacted shales, which will show anomalously low densities. For the limitations, the density log has a very shallow depth of investigation, making it sensitive to washouts, large borehole sizes, and thick mud cake. It's advantageous to have the density source loaded offset within a stabilizer to obtain an improved measurement due to borehole contact, and if the tool is enabled, to collect azimuthal data around the borehole as the tool rotates. As the tool passes bed boundaries, this information can be used to calculate formation dips. This slide highlights annulus pressure while drilling, or APWD, which is a key measurement for maintaining well control and monitoring downhole conditions in real time. Pressure sensors built into the MWD LWD tool record annular pressure as drilling progresses. The data is encoded and transmitted to the surface via mud pulse or electromagnetic telemetry, providing the rig crew with continuous monitoring. The primary function of APWD is to enhance hole cleaning efficiency, but it can also be used to detect a gas influx and for kick detection. The sensors are usually calibrated in the workshop before deployment, but can also be verified at the surface before being run in hole. They are highly reliable and designed to withstand the harsh downhole environment. The log on this slide is a sample output from an APWD sensor. It displays parameters such as cutting load, RPM, flow rate, and equivalent circulating density, ECD. The BHA in the hole is a motor assembly. What you can see is that in the slide sections, the ECD drops, but when the rotary is kicked in, the ECD spikes. This is because when sliding, the cuttings are settling out on the low side of the hole, which therefore is not part of the frictional losses that make up the ECD measurements. When the rotary is started, the cuttings become part of the fluid system, again heavily loading the hole and causing the spike in ECD. Starting with the advantages, LWD delivers data while drilling, which is invaluable for monitoring the dynamics of the hole in real time. This capability reduces uncertainty and allows quick adjustments. It is particularly helpful when steering through thin reservoirs where precise placement of the wellbore is critical. Another benefit is that LWD logs are less affected by mud filtrate invasion compared to wireline, meaning the data often reflects more of the true formation properties. LWD is also used to determine casing points by identifying intervals where casing should be set, and it highlights zones where additional wireline logging may be required for detailed evaluation. On the other hand, there are limitations. One of the biggest concerns is the cost if an LWD tool is lost in hole. Not all logging services are available in LWD mode, meaning wireline may still be required to complete the dataset. In addition, not all data is transmitted in real time. High-resolution measurements are often stored in memory and retrieved only when the tool returns to surface. Finally, LWD logs can be influenced by drilling effects and adjacent beds, and their resolution is typically less than that achieved by wireline. There are other logging while drilling services that complement the core measurements like resistivity, density, neutron, and gamma ray. These additional services provide critical inputs for wellbore stability, reservoir characterization, and geosteering. The sonic log measures the travel time of an acoustic signal through the formation. This information helps us calculate formation elastic properties and predict pore pressure, which is essential for safe drilling. Seismic while drilling integrates downhole seismic or sonic data with surface seismic surveys. By recording the travel path of sound waves through known formations, we can reduce uncertainty for deeper unknown intervals. This technique is especially valuable for depth tie calibration and precise well placement. The caliper log measures borehole size. This is important for correcting density and neutron measurements that are affected by borehole enlargement or irregularities. Calipers also support stress analysis by identifying borehole breakout zones. USIT scanning or ultrasonic imaging provides a detailed look at fractures, bedding planes, and formation dips, helping geologists map structural features in real time. Finally, integration of drilling data with geological interpretation, known as geosteering, allows us to steer wells optimally through thin or complex reservoirs. This is supported by interactive, multidisciplinary planning that ensures geologists, drilling engineers, and reservoir specialists work together for the best outcomes. To review this submodule, you should be able to define what logging while drilling, LWD, is, understanding both their principles and applications. You will also be able to describe the fundamentals of how these systems operate. Second, you should be able to list the advantages and disadvantages of LWD. Next, identifying sand and shale from log data. Recognizing lithological signatures on gamma ray and resistivity logs is a fundamental skill for geologists and engineers. Thank you for listening to this submodule 2 of 3. Please progress to the quiz.